In graph theory, the Bellman-Ford algorithm is a single-source shortest path algorithm. This means it finds the shortest path from a single source node to every other node in a graph. Unlike some other algorithms, Bellman-Ford works even with graphs that have negative edge weights, making it quite versatile. In simple terms, it helps us find the shortest path in weighted graphs where each edge has a certain cost or weight associated with it. グラフ理論において、ベルマンフォードアルゴリズムは多日現象最短経路アルゴリズムです。これは多日のソースノードからグラフのすべてのノード A の最低経路を見つけるという意味です。他のアルゴリズムとは違って、ベルマンフォードがネガティブエッジの重みがあるグラフでも動作します。これによって非常に多様性が高いアルゴリズムと言えるでしょう。簡単に言えば、ベルマンフォードは重さのついたグラフで最適経路を見つけるのを助けます。ここで重さとはぞらぞらのエッジにかかる比重やカカオを意味します。Now let's take a quick look at the history of the Bellman-Ford algorithm. Interestingly, this algorithm was first proposed in 1955 by Alfonso Schimbel, but it's named after Richard Bellman and Lester Ford Jr., who published it in 1956 and 1958 respectively. Oh, and there's a bit of a twist here. In 1957, Edward F. Moore also published the same algorithm. Because of this, it's sometimes called the Bellman-Ford-Moore algorithm. Here's a picture of Bellman-Ford and Lester Jr. on the slide. Take a moment to appreciate the people behind this groundbreaking algorithm. それでは、ベルマンフォードアルゴリズムの歴史を簡単に振り返ってみましょう。このアルゴリズムは1955年にアルフォンス・シンベルによって最初に提案されました。しかし、1956年当然、1958年にそれを発掘したリチャード・ベルマンとレスター・フォードの名前からベルマンフォードアルゴリズムと呼ばれるようになりました。思いがけり、1957年にはエドワード・ムールも同じアルゴリズムを発表しました。そのため、ベルマンフォード・ムールアルゴリズムと呼び出されることもあります。スライドにはベルマンとレスターの写真があります。この画期的なアルゴリズムを開発した人たちに感謝しましょう。Before we get deeper into the algorithm, let's first understand what we mean by shortest path. In a weighted directed graph, the shortest path between two nodes, say from node A to node B, is the path where the sum of the weights on the edges is the minimum among all possible paths connecting A and B. In simple terms, it's the quickest or least costly route between 2 points based on the weights assigned to the edges. This concept is fundamental to the Bellman-Ford algorithm, which ensures we always find that minimum path. アルゴリズムに深く入る前にまずは最小経路の意味を理解しましょう。重量式の優先グラフでは2つのノード的例としてノード A からノード B までの最小経路を A と B つなぐすべての経路の中で辺の重量の和が最小になる経路です。簡単に言えば、それは2つのポイントを結ぶ経路の中で一番早くまたは一番安く使うできる経路です。この概念はベルマンフォードアルゴリズムの基礎であり、いつでも最小の経路を見つかることを保証しています。Now let's talk about something called a negative cycle. This is a special situation in graphs that can create a problem for finding the shortest path. Imagine we have a cycle in the graph that's reachable from the source and has a negative sum of edge weights. What happens? Well, every time we go around this cycle, we reduce the total path sum even further. That means we can keep decreasing it endlessly and no shortest path actually exists. For example, consider the path 1 to 4 to 5 to 6 with the path sum of 4, but look carefully. There's a negative cycle minus 1 to 4 to 5 to 6 to 1. If we take another round on this cycle, the new path sum becomes 2, which is shorter than the first one. We can keep doing this and get a smaller and smaller sum. So whenever there is a negative cycle, the Bellman-Ford algorithm will detect it and let us know there is no valid shortest path. それでは、不平ルというものについて話しましょう。これはグラフにおける特別な状態で最小経路を求めるときに問題を引き越します。ソースからたどり着くことができるサイクルがあって、その辺の重量の側、ネガティブの場合何が起こるのか考えてみましょう。そのサイクルを1回回ったときに、パートの合計がもっともっと減ります。これは無限にパートのサムを小さくできることを意味します。そして最小経路は決して存在しないのです。例えば、経路1、4、5、6の合計は4です。でも、注意してみてください。ここにはネガティブサイクルがあります。マイナス1、4、5、6、1。もう一度このサイクルを回ったら経路の合計は2になります。これは最小よりもっと短いです。これを繰り返すことで合計はもっともっと小さくなります。それでは不平があるときはベルマンフォードアルゴリズムがそれを検出して最小経路が無効になっていることを教えてくれるのです。Alright, now let's see how the Bellman-Ford algorithm works. We can break it down into 4 simple steps. Step 1 is initialization. First, we initialize the distance from the source node to all other nodes. Initially, the distance to the source is 0, while for all other nodes, it's set to infinity. Step 2 is relax edges. This is the heart of the algorithm. We repeat the edge relaxation process exactly v-1 times, where v is the number of vertices. In each iteration, we check all edges and update the distance if we find a shorter path. Step 3 is iteration. During these v-1 iterations, we keep improving the shortest path estimate step by step. Step 4 is detect negative cycle. Finally, after all iterations, we perform one more check to detect any negative cycles. If no negative cycles is found, the algorithm successfully returns the shortest paths. But if a negative cycle exists, it returns false and warns us about it. それでは、ベルマンフォードアルゴリズムの動揺を見てみましょう。4の簡単なステップに分けます。ステップ1、初期化。ステップ2、エイジのカンマ。ステップ3、繰り返し。ステップ4、ネガティブサイクルの検出。Let's start with step 1, initialization. In this step, we assign initial values to the distances of all vertices. We set the distance of the source vertex to itself as 0 because obviously there is no cost to reach itself. For all other vertices, we set the distance to infinity since we haven't calculated any paths yet. それではステップ1、初期化から始めましょう。このステップでは、すべての定点の距離に初期の値を付与します。ソース定点の距離は0に設定します。自分自身に行くのにはもちろん費用がかからないからです。他の定点には距離を無限大にしています。これはまだどの経路も計算していないためです。Now we move on to the step 2, edge relaxation. This is the where the real magic happens. In this step, we go through every edge in the graph and check if we can find a shorter path. For each edge from U to V, we calculate the potential new distance to V by adding the edge weight to the current distance of U. If the newly calculated distance is shorter than the current distance to V, we update the distance of V with with this new value. We repeat this process for every edge during each iteration. This is called edge relaxation, and it's done v minus 1 times, where v is the number of vertices. Each iteration improves our distance estimates and brings us closer to the shortest path. それではステップに進みます。観点の計算です。これが一番重要な過程です。このステップではグラフのすべての観点をめぐってもっと短い経路が見つかるかどうかを確認します。例えば U から V へ進む観点を考えます。最初に U の現在の距離に観点の重さは加えて新しい距離を計算します。もしこの新しい距離が今までの V への距離より短かったら V の距離をこの新しい価値で改めます。この作業をすべての観点で繰り返します。これを距離の申請と言います。点の数を V とすれば、これを V-1 回繰り返すことで距離の推定がだんだん正確になって最終的に一番短い経路に近づいていきます。Next, we have step 3 iteration. In this step, we repeat the edge relaxation process v-1 times, where v is the number of vertices in the graph. Why v- times, you ask? That's because the longest possible shortest path in a graph with v vertices will contain at most v-1 edges. By repeating the process v-1 times, we ensure that every vertex gets the shortest possible distance from the source. Each iteration improves our distance estimates until we have found the shortest path for all vertices. すぐにステップ3に行きます。繰り返しの過程です。このステップでは観点の計算の過程をグラフの点の数から1引き高い繰り返します。なぜ1引き高い繰り返すのか質問しますよね。それは V 項の点があるグラフの中で一番長い最短経路が最多1引き高いの観点からなるからです。この過程を1引き高い繰り返すことで、すべての点が最終的にもって短い距離を得ることができます。繰り返すたびに、距離の推定がだんだん正確になっていくので、最後にはすべての点の最短経路を求めることができます。Finally, we come to step 4 negative cycle check. After completing the v-1 iterations, we perform one final pass through all the edges. This step helps us detect if there is negative cycle in the graph. If we find that any distance gets updated during this final iteration, it means there is a negative cycle. This is because the distance should not change anymore if we have already found the shortest path. In such cases, the algorithm will notify us and we can't determine a valid shortest path. If no distance is updated in the last iteration, the graph is free of negative cycles and the algorithm successfully returns the shortest paths. 最後にステップ4に行きます。負のサイクルの確認です。1引き高いの繰り返しが終わったらすべての観点をもう一度最後に確認します。このステップではグラフに負のサイクルがあるかどうかは検出します。もしこの最終の確認の時に距離がまた改まれることがあったなら、グラフに負のサイクルがあるという意味です。すでに最短経路が見つかっている場合は、距離はこれ以上変わるはずがありません。このような場合、アルゴリズムは私たちに負のサイクルの存在を伝え、有効な最短経路を提供できません。最終の確認で何も改めなければ、グラフには負のサイクルがないと分かり、アルゴリズムは成功して最短経路をしてみましょう。Now let's look at the pseudocode for the Bellman-Ford algorithm. It gives us a high-level overview of the algorithm steps. Step 1. Initialize distances and predecessors. For each vertex in the graph, we set its distance to infinity and its predecessors to null. We then set the distance of the source vertex to 0 since there is no cost to reach the source from itself. Step 2 is relax all edges v-1 times. We then perform v-1 iterations. In each iteration, we go through every edge in the graph. If we find a shorter path from a vertex u to vertex v, we update the distance of v and set u as the predecessor of v. Step 3 is check for negative weight cycles. After completing the v-1 iterations, we do one more pass through all edges. If any distance is still updated, that indicates a negative weight cycle in the graph. In that case, the algorithm will return a message saying the graph contains a negative cycle. If no negative cycle are found, the algorithm returns a final distance array and predecessor array, which gives us the shortest path and how to get there from the source. それでは、ベルマンフォードアルゴリズムの擬似コードを見てみましょう。これはアルゴリズムの過程を攻略的に説明します。ステップ1、距離と前の点の初期化。ステップ2、すべての観点を v-1 回繰り返す。ステップ3、負重さサイクルの確認。Let's go through the Java implementation of the Bellman-Ford algorithm step by step. Edge class. We start by defining an edge class to represent an edge in the graph. Each edge has a source vertex, src, a destination vertex, dest, and a weight. This class will help us store and access the edges in the graph. Second one is Bellman-Ford method. In the Bellman-Ford method, we perform the main steps of the algorithm. Step 1. Initialization. We create an array called distance to store the shortest distance from the source vertex to all other vertices. Initially, all distances are set to infinity except for the source vertex, which is set to 0. Step 2. Relaxing edges. We then iterate through all edges v-1 times, where v is the number of vertices. For each edge, we check if we can relax it. If the distance to the destination vertex can be shortened by taking the current edge. If it can, we update the distance to the destination vertex. Step 3 is check for negative weight cycles. After the relaxation steps, we perform one more pass through all the edges. If any distance can still be relaxed, that indicates the presence of a negative weight cycle, and we print an appropriate message. Step 4 is print the results. Finally, if there are no negative weight cycles, we print the shortest distance from the source to all other vertices. We use a helper method print result to display the results. Third one is main method. In the main method, we define the number of vertices and the edges of the graph. We create an array of edge objects, each representing an edge in the graph. For example, the edge new edge 0, 1, 5 means there is an edge from vertex 0 to vertex 1 with a weight of 5. ベルマンフォードアルゴリズムの Java 実行版をステップで考えてみましょう。Now let's look at the remaining edges and the output of the algorithm. In this code snippet, we define the remaining edges in the graph. New edge 3, 2, 1 represent an edge from vertex 3 to vertex 2 with a weight of 1. New edge 4, 3, minus 3 represents an edge from vertex 4 to vertex 3 with a weight of minus 3. New edge 0, 4, 8 represents an edge from vertex 0 to vertex 4 with a weight of 8. We then set the source vertex to 0 and call the Bellman-Ford method to compute the shortest paths. The output is, after running the algorithm, the output displays the shortest distances from the source vertex 0 to all other vertices. Vertex 0, the distance to itself is 0. Vertex 1, the shortest distance is 5. Vertex 2, the shortest distance is 6. Vertex 3, the shortest distance is 5. Vertex 4, the shortest distance is 8. それでは残りの観点とアルゴリズムの出力を見てみましょう。このコードのスプネットではグラフの残りの観点を定義しています。アルゴリズムを実行した後、出力は原種点からすべての他の点への最短距離を示します。Now let's talk about the time complexity of the Bellman-Ford algorithm. The time complexity for Bellman-Ford in the best, worst and average case is or V into E, where V is the number of vertices or nodes in the graph, E is the number of edges in the graph. In the worst case scenario, the algorithm needs to iterate through all edges for each vertex. Since we perform this edge relaxation process V minus 1 times, the overall time complexity becomes O V into E. So whether we are looking at the best, worst or average case, the time complexity remains O V into E for Bellman-Ford. This is more efficient than algorithms like Dijkstra's when we are working with graphs that include negative edge weights, but for very large graphs it can still be a bit slower. それでは、ベールマンフォードアルゴリズムの時間の複雑さについて話しましょう。ベールマンフォードの時間の複雑さは、財前、座具、平均の場合とも、O、V と E です。ここで V はグラフの点の数、ノードの数です。E はグラフの観点の数です。Now let's talk about the space complexity of the Bellman-Ford algorithm. The space complexity is O into V, where V is the number of vertices in the graph. This space complexity arises primarily from storing the distance array that holds the shortest distances from the source vertex to all other vertices in the graph. Since we only need to store one distance for each vertex, the space required is proportional to the number of vertices, making it O into V. Unlike some other algorithms that may require additional data structures, Bellman-Ford only needs this array to function efficiently. 次に、ベールマンフォードアルゴリズムの空気の複雑さについて話しましょう。空気の複雑さは O to V です。ここで V はグラフの点の数です。Now let's look at some real-world applications of the Bellman-Ford algorithm. It's widely used in several fields due to its ability to handle graphs with negative edge weights and its efficiency in certain scenarios. First one is network routing protocols. Bellman-Ford serves as a foundation for distance vector routing protocols like Routing Information Protocol. These protocols use the algorithm to find the shortest path between routers in a network, ensuring data is transmitted efficiently. Second one is traffic engineering. In network traffic optimization, Bellman-Ford helps identify the shortest paths between different points in a network. This is especially useful for optimizing traffic flow and ensuring efficient use of resources. Third one is financial modeling. The algorithm can be used to detect arbitrage opportunities in currency exchange. By analyzing the graph of currency conversion rates, it can identify negative cycles which represent potential profit-making opportunities through a series of exchange. 4 is logistics optimization. Logistics companies use Bellman-Ford to find the most efficient delivery routes. The algorithm helps determine the shortest path between various locations, minimizing travel time and cost. Fifth one is pathfinding in games. Bellman-Ford can also be used in game development for pathfinding, particularly in scenarios where there may be obstacles or negative weights associated with certain paths. It helps to identify the optimal path between points on a game map. それでは、ベールマンフォードアルゴリズムの現実のアプリケーションを見てみましょう。このアルゴリズムは、負重さ観点にも対応できることと、特定の場合での効率の高さからいろいろな分野で広く利用されています。ネットワーキングルーティングプロトコル、交通構想のエンジニア、金融モデル、ロジステックスの最適化、ゲームの経路真術。Now let's dive into the comparison between Bellman-Ford and Dijkstra's algorithm. While they share similarities, there are some important differences to consider when choosing between them for your specific use case. First one, main technique. Bellman-Ford relies on edge relaxation where V repeatedly checks all edges and updates distances over V-1 iterations. Dijkstra, on the other hand, uses a greedy approach where it always selects the closest vertex based on its current distance. Second one, time complexity. For Bellman-Ford, the time complexity is O V into E, which can make it slower for graphs with a large number of edges. Dijkstra typically has a time complexity of O into V to the power 2 when using an adjacency matrix or if implemented with a priority queue. This makes Dijkstra faster for graphs with fewer edges or non-negative weights. Third one works with negative edges. Bellman-Ford can handle graphs with negative edge weights, making it suitable for scenarios where negative weights are involved. Dijkstra, however, cannot handle negative edge weights and may give incorrect results if negative edges are present. 4. Detects negative cycles. One of the key strengths of Bellman-Ford is that it can detect negative cycles in a graph. If a cycle has a negative sum, Bellman-Ford will identify it. Dijkstra doesn't have this capability. Fifth one, optimal for sparse trees. Both algorithms are efficient for sparse graphs where the number of edges is much smaller than the number of vertices. In summary, if your graph contains negative edges or you need to detect negative cycles, Bellman-Ford is the way to go. However, if your graph has only non-negative weights and you want faster performance, Dijkstra is a better choice. ここからはベルマンフォードアルゴリズムとダイクストラアルゴリズムの比較に入りましょう。これらは共通点がありますが、特定の使用キー数に応じて選ぶ際に考慮すべき重要な違いもあります。1、主要な手法。ベルマンフォードは辺の緩和に依存します。すべての辺を何度もチェックし、b-1 回の繰り返しで距離を更新します。一方、ダイクステラは貪要約を使用し、現在の距離に基づいて常に最も近い点を選択します。2番、計算量。3番、負の辺に対応。4番、負の経路の検出。5番、総グラフに最適な。要約。もしグラフに負の辺が含まれているか、負の経路を検出する必要がある場合は、ベルマンフォードが適しています。一方、グラフが皮膚の重みのみを持ち、より高速なよりを望むなら、ダイクストラが適して選択です。